famous scientist hailing from India. He did some very vital work in both mathematics and quantum mechanics, mostly quantum mechanics. And today, I want to highlight one part of what he did for quantum mechanics and physics in general. Apart from the Bose-Einstein condensate, today I want to talk about Bose-Einstein statistics. But before that, let's get to the background of who Bose was. Now, he's often confused with Jagadish Chandra Bose, who was another scientist who came from India and, in fact, was born in the same region, but instead of working in quantum mechanics specifically, and instead of collaborating with a lot of the big names in physics at the time, and instead of gaining a lot of recognition, he worked on some parts of the radio receiver and didn't get too much recognition from physicists at the time. He didn't even win the Nobel Prize. So, what did Bose actually do? Well, it comes down to this. In quantum mechanics, as we've reviewed before, particles have little bits of quantized angular momentum called spin. Now, this was not known for a while, and we dealt with particles as if they had no inherent angular momentum, i.e. no spin or zero spin. So that was the classical interpretation of what was going on here. But of course, the classical interpretation was unfortunately wrong. Quantum mechanics tells us that every particle has a spin, and that spin is quantized on this ladder. This ladder going up and down in half steps. You can see why in one of our other videos. And every single particle with half integer spin is called a fermion, as you can see, named after Enrico Fermi, who also studied their properties. Everything left is a boson. As you can see, made from a combination of the word Bose, his last name, and on. Although the EO looks pretty weird for something that just makes an O noise. So it's just going to be boson. So, there we go. What's so different about bosons? Well, here's the picture. The Pauli exclusion principle is very important here. Wolfgang Pauli, or Pauli, I don't really remember how to pronounce it, found that when you have a particle by itself, its wave function is going to be normal. But when you have two particles, here's the problem. This can't be pushed down, something's blocking it. Okay. When you have two particles, something goes wrong. Here's the issue. Unlike regular particles, quantum particles that are in the exact same state are not distinguishable. You can't tell which is one and which is the other. You can't follow them around because that might change their state. Which means all of your physics has to be whether one is this and one is that, or one is that and one is this. Otherwise, there were two completely incompatible versions of reality, and it's totally random which we get, which means measurement has no meaning at all. And of course, that's catastrophic. Measurement has to have some sort of meaning. And of course, since there were more than two parts